And who told the elements where to go? Mendeleev!
The periodic table is an arrangement of the chemical elements devised by Mendeleev, ordered by their atomic number, electron configurations, and recurring chemical properties to show periodic trends. Hello, I am Mr. Mol, and today we'll be talking about how we group and count elements on the periodic table. The table can be broken up into 10 basic groups: alkali metals, alkaline earth metals, actinides, lanthanides, transition metals, basic metals, metalloids, nonmetals, halogens, and finally the noble gases. Each group of elements comes with its own set of properties. The first element on the periodic table is helium, a nonmetal, placed where it is because it's the simplest and most abundant element in the universe, made up of a single proton and a single electron. Helium is lighter than air, so it does a good job at lifting Zeppelin off the ground. But a word of warning: fly at your own risk. Alkali metals are highly reactive because they only have one valence electron, or electron in their outer shell, and they will force that electron on nearly any other element, reacting strongest with halogens, a group of elements missing only one valence electron from their outer shell. Now, the other day I was experimenting, and I found out something pretty interesting. It turns out that alkali metals have a property in common with common house cats, that being that, well, when exposed to water, they tend to react violently. Alkaline earth metals are also reactive because they're missing two electrons from their outer shell. Now, physically, metals are very diverse, ranging from hard elements such as aluminum to elements like gold, which are very soft and ductile. Ductility is how well a metal can be deformed when force is applied versus breaking into tinier pieces, much like how a regular duct will change shape if you apply enough force. All metals have very low specific heats, meaning that they are very efficient conductors of heat. Metals also conduct electricity very effectively because their valence electrons move freely when they're bonded. The next group of elements to be found on our periodic table are the nonmetals, which get their name because they're not metals. See, that wasn't that hard. Anyways, nonmetals are very important to you and I because they include elements such as the element carbon, which is the base element of all life on Earth. Without carbon, not you, nor I, nor anything else that's alive could exist. Another nonmetal, which is crucial to your existence, is oxygen, the stuff you breathe. Fun fact, oxygen can't be found by itself in nature. It needs to be bonded to something else. That's because it's part of a group called the Brinkelhoffs, a group of gases that cannot exist by themselves. Other nonmetallic elements include nitrogen, which makes up the majority of Earth's atmosphere. In between the metals and the nonmetals are a set of elements that share properties of both. They're called the metalloids. Just past the nonmetals is our next group of elements, the halogens. When an electrical current is passed through a halogen, it gives off light. More importantly, when halogens bond with hydrogen, they form nasty chemicals like hydrochloric or hydrofluoric acid. Lanthanides are also known as rare earth metals, and when exposed to the air, they tarnish. Actinides are also identified as rare earth metals, and some actinides, like plutonium and uranium, are used for nuclear power production. And finally, we have the noble gases, a set of elements whose outer shells of electrons are totally full and have no reason to react with any other element.
Who put them in columns and in rows? Mendeleev!
Since the beginning of time, weight has been a very important measurement in human society. It determines how much stuff you can, say, put on a cart before it collapses, or what materials you might need to build a weapon out of if you want to carry it long distances, amongst other things. Although measurements involving weight are useful in everyday life, they're ineffective in science because weight is only a function of how objects with mass are affected by different levels of gravity. Mass, however, remains constant because it's a measure of how much matter an object contains. So you don't need to worry about the mass of an object changing just because it's located somewhere else in the universe. Now usually, mass is measured in grams or kilograms, but these units are much too large to measure an atom with. It was obvious that a new unit of measurement was needed if they were going to understand the atom. Enter Avogadro. Well, almost. There we go. Now, some of you might think that with a face like his, nobody would ever want his number, but you would be sadly mistaken. Avogadro's number, this unholy behemoth, gives chemists a much better and more tangible unit of measurement, saying that 6.0221409 e to the 23 particles of any kind is equal to 1 mole. On the periodic table, every element has its own atomic mass. This mass indicates how many grams of a certain element you need to have 1 mole of that element. When two elements come together, finding out the molar mass is as simple as adding together the molar masses of the two elements. For example, the molar mass of the alkali metal sodium is 22.99 grams per mole. The molar mass of the halogen chlorine is 35.45 grams per mole. These two elements react to form sodium chloride, which has a molar mass of 58.44 grams per mole, the sum of the molar masses of the reactants.
Who was ready? Who was able to make a periodic table? Who was a chemist? Mendeleev.